OK. All right, the last few people are sitting down. Welcome to another Monday. We made it to another Monday. Amazing. Amazing, I know. I thought it was going to be close with the snow yesterday, but we're all right. OK, so today we're going to talk about review, because our midterm exam is on Wednesday. I'm actually not going to be here. I'm going to be winging my way to Kansas City, Missouri. Anybody from Kansas City or Missouri in general? I don't know much about Kansas City. I've been to Kansas City, Kansas, and not Kansas City, Missouri. So we'll see. It's for a conference on computer science teaching, so apt, I suppose. Let's see. So a couple things going on this week. Midterm is Wednesday. Let's see. The homework assignment. So I've got my inbox has started filling up with people saying, oh my gosh, we've got so much to do this week. So this is a pretty big week for people, isn't it? I didn't realize it'd be this kind of huge. What I was thinking about was, so I'm going to be gone till like Sunday. There is no way we're going to start grading any assignments until at least Monday. So would you guys want an extension till Sunday? That help? OK. So that'll help alleviate a little bit of the pain, I hope. As far as TAs, there'll be TAs still, at least on, there will be some TAs on Sunday, none on Saturday at this point. But hopefully the project's going OK. Those that I've already looked at, people who have talked to me about them, they seem to be all right. I'm going to go over a couple of ideas. I mentioned this the other day. Remember the remove function for the two-child node in a binary search tree is actually tricky to write, but there's definitely some very specific things you have to consider when you're writing the one for R's. Namely, you have to be very careful about when you actually go about changing the data, number one. And number two, if the child that you are actually promoting up into the node you're removing, if that has multiple count greater than 1, you have to be careful. So I will go over some of that on here. OK? And you'll be able to ask questions about that. And if you don't quite get it, you'll understand when you start programming this. You'll go, oh, that's what Chris is talking about. Now I get it. OK? Questions before we get going? OK. So here's what we're going to do. A quick Unix tip of the day on the zip command. And then review for the midterm. In the middle there, we're going to, or right at the beginning, we're going to talk briefly about this binary search tree stuff. And then at the end, we'll go over, actually, I'll show you last semester's mid-year exam. And then it's actually online, so you can see it. And the key is online as well. Keep in mind, it's got to be, this one's going to be different, but the format will be very similar. OK? Some of the questions will be similar. And I'm not trying to trick you on this test. I just want you to show me what you know and prove that you can write through programs and things like that. OK, quick Unix tip of the day. So you guys have seen zip files before, I assume, right? A zip file is what? It's a compressed version of a folder or a file or something. And what you can do on the homework server is you can actually zip up your, let's say, your comp11 files. Let's say you want to keep a copy for yourself of your comp11 files, and you want to keep it on your own computer, or you want to free up some space or something like that. You can actually zip up your comp11 folder using the following commands. Zip-r means recursive, means go through and zip everything in the following folder, to a file called, in this case, comp11.zip. And that's the actual file it's going to be in. And then the name of the folder you're zipping, /star means everything in that folder. And let's say you didn't run the cleanup command. You still have core files in there, but you don't want the core files to go into your zip file. This -x means exclude files that meet the following pattern: anything, core, anything. OK? So that's the way you could do that. And then you could go and delete the comp11 folder. I had a student a couple semesters ago who did this. She actually did this for her comp11 and comp15 folder. And for whatever reason, she had never, well, there's lots of reasons, but she hadn't submitted her final assignment to me. And she zipped them up, and then we worked it out later where she was going to send me the files and whatever. And she went to look at her file, and she had typed this command wrong, and there was nothing in the zip file. And she had deleted it, and it was like well after they kept backups, so never got that to me. So anyway, be careful with it. You might want to just check. I'll show you. You might want to just check to make sure that the file actually worked the way you think it did. Yeah, check before deleting. Let's see. So let's go to the homework server here. Let me go to the top of the screen. OK, I think I actually just created this for the other class, comp11.zip. Yeah, so I happen to have a comp11 folder here. And let's say I'm in one folder before it. If I type zip-r for recursive, and then comp11.zip, and then comp11/*-x star core star means remove the core files. And then I do this, it will tell you all the different files that are getting zipped up here, right? What's interesting is some files, it tells you how much it was able to compress, because this is a compressed format. Some of them are like 99%. Your text files are easy to compress. Files like PNG files or JPEGs, 2%. Anybody know why that's the case? Why you can't compress a JPEG or a PNG file very much? What do you think, Janelle? Yeah? JPEG's already compressed. So are PNG files. They're both already compressed, and they do a really good job. That's why they're standards, right? And so you can't compress them much more. I used to think when I first started talking about compression things back when I was like in high school or something, I would think, what if you zip a zip file? Can you get like extra compression out of it? And like you would try this, right? But it would only zip, the first time it would zip like 90-something%, and then it would zip like 1 or 2, maybe 0%, depending on that. So there's reasons why you use JPEGs and PNG files and GIFs and that sort of thing, because they're already compressed. Yeah?
If you can compress that text file so much the way they currently are, why not still get all the data? Why not have all of them be that compressed in the first place?
Yeah, that's a good question. Why not already have that? There are some systems that will do that sort of thing for you. Like it's actually, in some cases, for big files, it's actually quicker to load a compressed file into memory and uncompress it in memory than it is to like leave it on disk and in the compressed form or in the uncompressed form. So there are things that do that. So it's an interesting idea. Most of the time, it's a little too much work than you want to deal with. Like that layer of compression decompression is not necessarily the easiest thing to get right. So people don't generally do it. And we've got hard drives that are huge now, so it's not quite as big of a deal. Yeah. Good question. tar.gz is roughly the same as zip. I mean, it's not. You probably won't see much of a difference. You might get 1% here or there, but that's about it. All right. Yeah. You can look those things up. When you guys get to Comp 40, for those of you who are taking Comp 40, you will study all about compression, and you'll actually write a little compression algorithm to compress some things. It's kind of fun. It's a fun assignment. Actually, I hear it's the hardest assignment, but it's fun anyway. It's kind of neat stuff. Other questions on this stuff? OK, so that's the zip file. And then you could copy it to your thing. And by the way, you should always check ls-al comp11.zip and make sure that it's not like 0 length or something, right? And if you copy it to your own computer, unzip the copy there and just see that they're all there, and then delete that and have the zip file still. So anyway, questions on that? OK, that's the Unix tip of the day. All right, so let's see. I'll pause on the midterm tips. Let's talk briefly about this removing the double child node. OK? I already mentioned these. There are a couple things you need to consider. If you've already written this and you got it right, awesome. You can lay back and be smug and whatever. But in terms of if you haven't thought of this yet, we're going to go through 2 examples. And when you have to consider, like I said before, when you actually move the data. I'll show you what that means in a minute. And what if the recursively removed child actually has a count that's greater than 1? It's kind of a special case. OK? So let's take a look at this. Let me write these down so that we can do this. Let's see. 14, and then 7, and then 17, and 4. And 12, and 11, and let's see, 16 and 53. 16 and 53. OK. We are going to try to remove 17 here. Now, we're actually going to get a little bit more detailed, because you've got to think about these things. Yeah, a little bit more detailed into the actual code of what pointers are going to change and how things are going to change, because you're going to need to think about this for your programming for your assignment. OK? All right, if we're removing 17, OK, first of all, we do the checks that say, look, is 17 a leaf? It's easy to remove. If 17 only has 1 child, it's pretty easy to remove, right? If 17 has a count of greater than 1, it's really easy to remove, right? You just decrement the count and you're done, right? But in this case, 17 has 2 children, and you've got to do something like special. Yeah?
So if you run the remove function and it says to remove 17,
Mm-hmm.
are we basically removing just one count of 17 or removing the whole node? Let's say that this is 17.
You're removing one count of it. If you remove, if you say remove 17, you're not removing all the 17s. You're just removing that one count of 17.
So there could be 17.
There could, if this had a little asterisk in the little printout and the count was 5, the count would then be 4, and everything would be fine. OK, yeah. If you've, I think I believe we check for that. I think we do. But anyway, that's what it should do. Anyway, OK. I just realized it's hard to see this from over there in that corner, isn't it? A little tricky. Sorry about that. Should probably move to the middle board or something. OK, I'll try to like write bold. I don't know. OK, so for removing 17, it's got 2 children. And we have to do this special case. Now, what was the algorithm we used to remove a node that has 2 children? This is the one we all discussed for a while, and we landed on one that works pretty well. And it's the one I'd like you to use. What is the algorithm? Yeah?
So you find it, and then copy all the comments and find it of the node you're trying to remove.
You have to be a little more specific. Which minimum are we finding?
So the minimum of the node you're trying to remove.
Not quite, no. We're not going to do this one. It's going to be which one? It's the minimum of the right child of the node you're trying to remove. OK, so you're close. Yeah, it's the minimum of the right child. Now, in this case, this happens to be kind of a special case because of what I'm going to show you. It's not a special case, but you have to handle all of them as if this was a special case. If you're trying to find the minimum of 53's nodes, what is the minimum of this subtree? 53. So this is the one that we're going to eventually remove, but we're going to move the data from here up to here. Does that make sense? OK, so this is what we have to do to think about this. Now, you just said take the data from this one and replace it with 17? Or put it in this node? Maybe you didn't say that. You hadn't gotten there yet.
The data of the
Yeah, the data of this one replaces the data of the one you want to remove, right? OK, so it's going to be, instead of 17 here, it's going to be 53 here. And then what are you going to do? You're going to remove 53. OK, and you're going to do that recursively. In other words, you're just going to call remove on this one's right child. OK, now, this is where it gets a little bit where you have to, once you code this, you'll go, oh, I get it now. How do we decide? Well, first of all, this node has 2 children, and with only one node here, what is this node's, which of this node's children is going to get null after this is complete? The right one. So this is going to be null eventually. Now, how do you decide, if you know that you've got 53, how do you know if its parent was if it was a right child of its parent or a left child of its parent? How are you going to figure that out? It does matter, because 53's left child is going to remain 16, but 53's right child has to become 53. How do you know it's going to be 53? Yeah?
Well, since you just copied the data, you want to compare the values of each of the children and see if
Oh, that's a good idea. That's one way to do it. You could compare the, now if you've already copied the data, you can compare the data and see if it's the same. That's a good point. I was thinking of a slightly different idea, but that's not a bad idea. Yeah, Sarah?
That's not going to work if it's further down the tree.
Yeah, that's a good point. If it's further down the tree, well, no. Oh, yeah, you're right. It would, because you'd have to walk down the tree to do that. So that's, yeah, good idea though. I think there's a slightly more robust thing to do. Yeah, Winona?
Can't you recursively call the same remove function, but instead of passing the root again, you just pass the right node of that? Like,
Of this one?
yeah.
Well, the problem with that is we're going to have to eventually change this one's right to point to this node, to be null. Right? So that's going to be careful. Yeah?
Well, does the remove function also get the parent?
It will get the parent. But what I'm saying is, how do you know if this was, let's go back to this. How do you know that 53 is to the right of 17 and not the left of 17? Yeah? Because 53 is greater than 17. What if you had already changed this to 53? Then you're in trouble because you're not sure they're the same. So this is the key now. So here's the idea. At least this is the way I would do it. In fact, it's probably the way I did do it. Before you change this value to this one, do the remove on this one. But what do you need to store about this one first? Store its value and also store the count, which we'll say in this case is 1. So if you store that, now if you just straight up remove this one, will it remove properly? Yeah, it'll remove properly, and you don't need to do anything else about it. Well, we'll see on the next slide that you might have to do one other special case. Yeah?
How do you feel about just moving the attachment from the 14 to the 53?
Well, the problem with that is then this one has to also go. And then what if there's stuff? Well, there won't be anything down here, I suppose. So you're right. I mean, you could. You definitely could.
But stuff between the 17 and the 53.
If there's stuff between the 17 and the 53, you're going to be in trouble, because this could be down here somewhere. So you just have to be a little careful. But bear with me on this. I think it's easier if you just change the data. But store the data, remove this one, and then put the 53 here with the count of 1. Does that make sense? I think that's the best solution here. I think you won't rip out as much hair if you try to do it that way.
So what if
Okay.
the count on the 53 was
Yeah.
one length of-
This is a good question. So Isabel's question is, what if the count is actually, say, the count is 3 or something? Now we've got, this is actually the next thing here. If the count is 53, then we do have a special case. Because what happens if you remove 53 with a count of 3? What do we say that it does? It just decrements, and then 53 remains. So you have to be a little more careful. And that's actually, it's actually tricky given the way we've set this up. But you have to be careful that you officially remove this whole one. OK?
actually move it still?
You still move the 53 and the count of 3 up here. But this whole node gets removed. It doesn't just get decremented. You have to still remove this one. OK? There are various ways of doing that, but you have to do it.
And you don't subtract from the.
You don't subtract that anymore. No. You just move that whole thing up to there.
Removing it, you're just removing.
Right. You're not removing it. Well, right. You're officially removing this node, but the actual node itself kind of gets replaced up here, or moved up here. You're kind of officially moving it, not removing it, if you want to think of it that way. But the point is that you have to be, those two cases will get you mixed up if you're not paying attention. OK? Other questions on that? Did that make sense? Try to remove this one, but if you remove this one with a count of more than 1, you're going to be, this one's going to remain. Yeah, Nick?
So what you have to do is just set the count of that one equal to 1 before.
That's actually a great way of doing it.
But
Yep.
you have to save.
Save the count of 3. Make this one have a count of 1, so it officially gets removed. And then remove it. Then update this one to 53. That's exactly the way I would do it. Yep, good call. Yeah?
Could you also keep recursively calling remove if the count's greater than 1?
Could you? Yeah, you could. You could keep calling remove if the count's greater than 1. I wouldn't suggest that way because it's not the. It's not too. Actually, that's not too slow because remove is really delete, decrement, decrement, decrement. Yeah, while the count is not 0 or whatever. Yeah, I guess you could. Either way would work fine. I really like Nathan's suggestion of just saying, look, fake it out, make it 1, remove it, and then make sure to update this one to back to 3. Yeah, good call. OK. Any other questions on that? Yeah, Alexandra.
So 53, sorry, 53 by a child,
Which child, right or left, makes a difference?
left,
Then it wouldn't be the min, and we wouldn't worry about it at all.
right. And then,
Correct.
So you would just bypass, you would leave the point.
Yeah, let's say this was, let's see, what could this be? 20.
Yeah.
Let's say it was 20. Well, which one gets replaced up? The 20 now replaces this. And you remove 20.
And 53 just stays.
53 stays, yep, stays perfectly fine.
So what if it were the right child?
OK, if it were the right child, let's say it was 60. If it were the right child, then look, 53 gets removed. But how do you, well, first of all, you'd be replacing 60 up here, right? And this would just get decremented. Sorry, I lied. Sorry, I lied. This would get up there, and then this would just be deleted. No, I'm still wrong. What am I talking about? This is the minimum. I lied. This is the minimum. OK. This one goes up here. The 53 completely goes up here, right? And now this one ends up connecting to this one. You see? Yeah. It's because this one can't have 2 children if it's the minimum.
Okay.
Right?
Yeah.
Did that confuse anybody? Sorry. I'll say it again. This is the minimum of the right child. right? To remove this one, you basically are going to end up bypassing like this and moving that data to there, right? Again, you would want to make that count 1 if it's not already and can store it. Yeah?
How many edge cases are there is you can concern with?
All of them.
I'm no obviously, but I'm just thinking like if it has its own sort of tree underneath it, like left, right, all the kinds.
Well, this one can't. Remember, it can't have lefts. Well, it could, but if it did, this would now be the minimum.
So then what if that has you're still
Which way?
both?
OK. Let's see. Let's see if I can get this right. 40 and 18. OK, which one's the minimum now?
18.
This one is. So this one replaces the 17 and gets recursively deleted.
But
Right?
you don't have to change anything.
And you can't have anything to the left of that, or it wouldn't be the smallest. If it had something to the right, is there anything left? 19. Right? If it had something to the right over here, then this would be recursively moved, so this would now point down here. But it does, that happens already if you're removing 18. If you remove if you write the remove function, it will work correctly to remove 18. The only corner case in this situation is if 18 happens to have multiple count. Then you need to do like what Nathan said. He said, just fake it out, change the count to 1 initially, do the remove. That'll remove it fine, and then update this to be the correct count. OK? Yeah, good questions. Can you see why I gave this assignment to you? It's not to make you rip your hair out. It's to like make you think about these things.
So is stuff like this valid, like for test?
Is stuff like this valid for the
Or
test?
like fair game?
I mean, it's fair game, but I'm not going to, I don't think I'm going to be like, I kind of want to test you on a lot of different things. If you're already doing a lot of this for your homework assignment, I'm not going to sit here and like make you do it all on here. I don't think that makes too much sense. OK, other questions on that? OK. Please put questions on Piazza or come to office hours or whatever, or email me. We'll figure it out if you still have questions. OK, so the mid-year exam. All right, so I did put last semester's online. You can check it out. We'll check it out at the end of this class. It's going to have some short answers. Explain a case for using a linked list. It's better than a dynamic array, et cetera, et cetera. The answer is never. No, you could say in particular. There's some cases. But you'd have to do short answer stuff. There's going to be find the bugs in the code. I think the hardest ones of those are when you have to find bugs that don't exist. In other words, it's supposed to be doing something, but we forgot to put something in. That's hard to find, right? Because you got to know to yourself, hey, wait a minute, they should be doing this, and they didn't. So that's tricky, but you have to find some bugs in code. There will be some short code writing, possibly a data structure you haven't seen yet. I threw that in there in case I find a cool data structure that for instance, a couple years ago, there was a question on a 2-3 binary tree that, or maybe that's not a binary tree. I don't even know. But it was on a 2-3 tree, and they explained a little bit about what it was, and then the students had to like create the class like on the test. That would be a hard problem, right? I'm probably not going to do that, but you should be, not that you can really prepare for that. But I'll make it so that you can, that you're prepared, that you are prepared for it from what we've already talked about in class. Please don't stress about that. But the short code writing, you will have to write some short code. Plan on writing something that's recursive, OK? And that'll be that. Explain what some code does. Also determine big O bounds, asymptotic complexity. Somebody posted on Piazza, like, how do we do that for programs? I'll show you a couple examples that will see that. And then explain some C++, right? The big C++ things we've talked about. I count 5 new things that you might not have seen before. Destructor, operator assignment overload, copy constructor, const, and what was the other one? References, pass by reference. Pass by reference and const I'm probably not going to ask you about. I'll tell you that right now. OK? You did pass by reference in Comp 11? OK. With references, with the ampersand? OK, well, anyway, the point is that we've talked about those things. Those are kind of the big C++ things. OK? All right, so those are the types of problems you'll see. Here's all the topics we've covered. Memory management, C++, memory management, arrays. We did lots of stuff on static and dynamic arrays, linked lists, OK, recursion, did some on recursion, and you've done lots of recursion for this assignment, right? Somebody asked in the assignment today, or in Piazza, about can we just keep track of the number of total nodes in the tree or whatever, because so we don't have to call that function. And my response was, that function you're talking about to count the nodes in the tree is like 2 lines long. So I mean, you can. It would take a little bit of time, but it's all logarithmic. Well, actually, in that case, it's linear. But the point is, don't go making more work for yourself if writing the recursive function is easy. That's all I'm saying. You can, but keep in mind it'll be more work. Stacks and queues. We had a whole assignment on queues. You should know those pretty well. Stacks, we've done some work on stacks, and they're not that advanced anyway. And then all sorts of stuff on trees we've talked about, general trees, binary trees, AVL trees. And then there's asymptotic notation that we'll have to talk about. OK? So let's go through some of those. C++. Destructors, dynamic versus automatic memory. So we haven't talked about automatic memory, but when you use the new command, that's for dynamic memory, dynamic arrays, et cetera, right? If you just say something like, stack s, right? That's using what's called automatic memory. In other words, you don't need to delete it. You don't need to worry about it. And it's only good for the function that you're in. That's the only time it's good for. OK? So if you need to keep it after your function, then you'd better make it dynamic. Or if it's a class variable that internally takes up, does all the dynamic stuff, then you don't need to worry about it. OK? That's what that's all about. ADTs, you should know the difference between an abstract data type and a data structure. Abstract data type is basically the interface. Data structure is the actual underlying structure of the code, like if it's an array or a linked list, et cetera. Okay. That's about it for C++. Yeah.
Did you, so which one is a queue?
A queue, you tell me. Can I build a queue? Can I build a queue with different? How many? Just out of curiosity, how many people used a linked list to build their queue for the assignment on queues? A couple people. Last class was about 10%. It's only about 5%, not even. And then how many people used dynamic array? Nice. How many people thought of using some other data structure that we haven't talked about? Oh, you could have. Did you?
I did not.
OK. You wanted to. OK. So yeah. So what do you think? If part of the class used a different underlying data structure, then what's a queue? Abstract data type. Why? Because it defines the interface. What are our 4 things we can do with queues?
Push.
Nope, not push. Close though. Oh, actually, I suppose you can push if you're talking about the queue that we used in the standard template library. But we're calling it what? InQueue instead of push. But yeah, I would probably accept push. So InQueue, DQ. What's the other big one? Is empty. And then there's one we sometimes use. Front or top. Yeah, front is generally the one we use. You could also have a back if you wanted, right? But yeah.
Do you need a destructor for an object where all of the memory for it is automatic?
Good, very good question. I bet you answer that in 1 second on your own. Hold on. Hold on to that in 1 second. Look at that. It's like you're looking ahead. I know you're not, though. Do this. Answer that question right here. Do it right now. Either write out a little answer or talk to your neighbor about when is a destructor necessary in a C++ program, and when is it OK to use a default destructor? The default destructor is the one the compiler creates for you. And here's what it is. If it was a queue, it would be queue tilde queue. And then it would be doesn't do anything. Creates it for you, but it doesn't do anything. Not quite, but almost.
I guess you wouldn't need it if you delete using certain functions. Like if you delete the new thing using the functions that you use the new in.
Yep. Yeah. Right.
But if you're using new in your header file, or like in your,
Well, not in your header file, but I know what you mean. In your, most likely, yes. Yeah, most likely, yes. OK, who has a good answer for this? Isabel, you and I just talked about it. Who else has a good answer? Somebody from like this side of the room. I haven't seen anybody over here lately talk. Yeah, what do you think, Tafari?
We were just saying that, like, we thought about text usually it might be using dynamic memory.
OK, so you're using dynamic memory. That is a key thing. As Alex was saying, if you don't use dynamic memory, you never need to worry about a destructor, right? If you always use automatic memory, then there is nothing to delete and to clean up for afterwards. OK, but even if you are using dynamic memory, there are some cases where you might not have to use a destructor. Can anybody think of an example there when that would be the case? OK, Isabel.
Basically, when you have you use new, for example, in an expand function.
Yep.
And you use it, but then you call delete on the thing you call new on at the end of the function.
Yeah, almost. So Isabel's answer is, look, if you're using new and then at the end of the function you call delete on that thing you just used new on, I would argue that you probably wouldn't need to use new to begin with. You might, but you probably wouldn't need to use it to begin with. But that's OK. But it's a little more subtle than that. If when your program is or your class is going to be destroyed, if you still have remaining memory that you used new on that nowhere else it was destroyed, then you have to have a destructor. In other words, as if you're getting to the end of your class and something that you did called new on has not yet been deleted, it needs to be deleted in the destructor. That's when you do it.
So how do you know?
How do you know? The logic of your program dictates it for you. But it's a subtle point. But the idea is in the queue that we used, if you did a dynamic array for a queue, or even if you did the linked list, at the end of the class, when nothing else, when main ended, you've still got this queue that you've created, and that needs to be destroyed, right? So that's when you need to, if some piece of your data structure remains, that's when you use destroy. Then you use delete. Question?
If you write a destructor but you don't need it, will you get errors?
If you write a destructor and you don't need it, well, depends. If you let's use an example. Let's say you built your queue with dynamic array, and you in-queued a bunch of stuff, then you de-queued everything, and then your queue at the end had no nodes left, like head pointed to null. You'd still need a destructor, because what if you hadn't de-queued everything? That's the first thing. But if you
What if you delete it in main?
well, hold on. Well, if you delete it in, you can't. Well, you could delete it in main, but you wouldn't have access to it because it's probably a private variable. But point is, if your destructor should take into account the fact that maybe my linked list has no elements in them. That's all. OK, you'd still need to write it, but it wouldn't actually do anything if there's nothing else to delete. Yeah, Katie.
When you use a destructor, what's actually happening in the memory?
Yeah, good question. So the destructor's a function. It's just a function that gets called when the runtime is cleaning up after itself. OK, sometimes it doesn't know how to clean up after itself because you've created dynamic memory and it can't figure it out. Right? There's this thing called garbage collection. It's kind of a funny name, but it's called garbage collection. Some languages have that built in. For instance, Java has garbage collection built in. So you can say new all you want. And Java keeps track of all the times you use new. And at the end, it says, oh, I can clean up after this. Right? Why does Java have it and C++ not have it? Any ideas? Yeah?
Java was built for machines with more memory.
Java was built before machines with memory? No.
Okay, Java was invented later on.
Oh, when machines had more memory. Well, which leads you to the idea that maybe garbage collection takes up a little more memory to figure out. But it's also, there's one other big thing about garbage collection that people don't like it for. It's what? What? It's time consuming. It's slow, right? If you know exactly when you're going to be removing stuff, you can control a little bit more about your program. So C++ allows you to have more control. What does that really mean? It means it's harder, right? But this kind of gets back to the idea of why do we teach C++, like data structures in C++? Most schools don't do that anymore, actually, right? They teach it in Java or Python or some other languages. Part of the reason we've stuck with it, and that may change going down the line, but part of the reason we've stuck with it is so that you guys learn a little more about the underlying computer architecture about like, hey, there's an array down here that somehow somebody has to take care of. Any Java programmers in here? From anything? Yeah. You guys know about the array list class in Java? It's basically a dynamic array that handles everything for you, right? But under the covers, guess what? It's got a real array that it has to expand and contract, and it does all that hidden from you, right? So if you don't know about that, you won't really understand it, and that's kind of why we want to teach you a little bit more low-level stuff. Okay, is that the best answer in the world? I don't know, but it's my answer. Okay, all right, good. Let's go on. Here we go, static and dynamic arrays. So static and dynamic arrays, we have talked a lot about this, right? The static ones are the ones, if you say something like int my array 10, that creates an array of 10 integers, and you can't change it, and you don't need to change it. And at the end of your function, the compiler takes care of deleting it for you. All right, that's a standard static array, and the dynamic ones we've already talked about. You use new, you can expand them, etc. Okay. Arrays have indexes that allow constant time lookup. Well, that's kind of nice. You can say my array 4, and does that need to walk through the entire array to get to 4? No, it's constant time. Okay, so that's awesome. Why are arrays in general good? A couple answers for this. What do you guys think? Yeah. They're simple. That is actually that's actually an underlooked kind of like a rarely mentioned one, but that's a good one, right? They're pretty simple. They're one long piece of memory. You can access them randomly, and that's it. None of this like weird pointer baloney that you have to like point various parts to. That's a good point. Here. If you have an index, you can go backwards. It's not so much that you can go backwards, but we have random access, right? You can go 4 and then 2 and then 9 and then whatever without walking through anything. Yeah, that's definitely an important one. Okay. Downsides to using arrays, or you got another upside?
I was going to say like inserting it is like, pretty OK if you're just filling the array.
Good question. Where do we want to insert into an array to give it constant time behavior? At the end, right? If you insert at the beginning, what kind of behavior do you have? Linear behavior if you've got to keep it in order, right? You could do some fancy stuff where you swap things, but if you needed to keep it in order, you have to move all of them. So that's kind of one of the downsides, right? Inserting at the beginning of an array is not fun if you want to keep it in order. OK, the next line gives you another kind of downside in some sense. It's an upside and a downside. Expanding. The good news about that is you can do it, right? If you need more space, you ask the memory system for more space using new, and it gives you a new array. The problem is you can't just extend your array, right? You have to actually copy all the elements from one to the other. OK. And then the asymptotic behavior, we kind of just talked about that. Constant if you insert at the end, constant for indexing into it, and linear if you have to insert at the beginning and keep it in order. OK. Sample question. Write the insert function like insert at the beginning. What's the basic idea there? Yeah, Boris. OK, can I go through this array to insert and go A goes here, and then B goes here, and then C goes here? No. You can't do that. So you actually have to do what? You have to start from the end and move C here, and then B here, and then A here, and then insert your next one there, right? So it's a little tricky. There's a couple like things you have to worry about. Yeah?
When we're saying let an insert function for a dynamic array, are they specifying specifically that you need to put it in the front, or can you just say like?
I would be specific about it. Yeah, I would be specific about it. But what's the first thing we do in an insert? Check if it's to a need to expand. And then you'd call expand. I wouldn't make you say write the expand in that case. But I'd say call it. Yeah. Did you have another question, Alexander?
No,
that was the point. You said, hey, you forgot to expand it. Yes, we did.
What if it's circular? Like, would you distinguish?
What if it's circular? A circular array?
Like, would you distinguish distinguish what type of an empty we're working with?
We generally don't have circular arrays. Well, we can, but they're more queues generally. But right, you would have to be more specific if we wanted to. Yeah. Ooh, there's a good question. Circular array. Thanks. OK, any other questions on this one? All right. Linked lists. OK, so linked lists, remember, the reason we showed you these is because it's a linked structure. All things considered, it's relatively easy to understand. Not necessarily easy to program linked lists. You guys found out that when you were doing the second programming assignment, right? You've got these nodes, and you've got to link them properly. And you have lots of corner cases with a head and possibly a tail and all that. Linked lists, you have to walk through them. There is no random access in a linked list. Heads and possibly tails, special cases, blah, blah, blah. You should be able to, for the test, reason through a linked list operation with a picture. In other words, draw out a number of nodes, or I'll give you a bunch of nodes, and I'll say, what pointers need to change to have everything, to remove this object or whatever, to remove this node. OK? Deleting a node in a singly linked list. You better have the previous node, or you've got to walk through the whole list again to get there. Right? You have to, because there's no going back in a singly linked list. Yeah?
Sorry, to back up a little bit. What happens if you call delete on something that isn't in the heap? On memory that isn't in the heap? Does everything crash? Does it just ignore it? Or?
You'll get a compiler error is probably what you will. You're probably not allowed. If you tried it, you'd get some sort of free error. Yeah, you get an error either way. If the compiler didn't pick it up, when you ran it, it would pick up. Yeah, if you try to delete something in the stack instead of the heap. Yeah, good question. All right, so anyway, linked lists. So that's singly linked lists. Doubly linked lists, remember, you've got pointers going both ways. They're better in the sense that, hey, you can walk both ways, and you only need the one node. You don't need a previous or a next to delete it. But remember in that lab where you guys were all like grumbling about, oh my gosh, we got to move this pointer and this pointer and 4 pointers? You weren't grumbling. But it's kind of like, this is annoying because I have to keep track of everything. Lots of bookkeeping in doubly linked lists. Right? They're tricky. Operations are definitely tricky. One of the downsides to linked lists, they're not the easiest ones in the world to get right. Not impossible, but you have corner cases and things. And then we do have circular linked lists, which basically means the tail points back to the head. You have to be a little careful if you're trying to walk through it that you remember to keep the one you started on, or you'll just go forever. But we definitely can do that. OK? All right. That's linked lists. Question on linked lists. I might ask you to find an error in a linked list implementation. This would be tricky. I think I did that a couple semesters ago, and it's not the most fun because you got to really keep track of everything. And yeah. Anyway, that would be a sample question. Okay. All right, so recursion. You talked about recursion in Comp 11. We reviewed a little bit here. I will ask you to program something that's recursive, or write out a little recursive program on the test. Recursion is not magic. It just means calling yourself, but it's tricky to figure out. Right? I'm going to ask you to try to write a little function in a minute, and it's a little bit tricky. Not impossible, but a little bit tricky. Okay? The compiler handles recursion in a very stack-like way. Right? In fact, it uses the stack for recursion, the stack. And remember, if you're calling a bunch of functions, the last one that you called is the first one that returns. Right? Back, 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 back. So that's a last in, first out method. OK? You should definitely understand recursive functions. And here's some examples. Fibonacci. Why was the Fibonacci sequence bad? The first one we created? Anybody remember? Yeah, Katie?
Because when you do the tail call, you're calling 2 recursive functions, so you're reducing exponentially.
Yeah, when you make that last call, you call Fibonacci twice on redundant data in some cases. So it's exponential behavior, which is terrible. Right? There's better ways to write that one. Beautiful, but terrible at the same time. OK, so those are some ones there. So here's a good sample question. Write a recursive function to calculate the sum of the first n even numbers. In other words, I'm going to give you n, and you want to add up the first n even numbers. Should we start n at 0 or 2? Because 0 is an even number, right? Let's start at 2. go ahead and write this. Try it right now. Or talk to your neighbor about how you'd write it if you don't want to actually write it out. But try this. I'll start it on the board. And by start it, I mean write the function name.
So you're giving us multiple ends?
No, I'm going to do this. Sum evens. And I'm going to pass in an integer, n. Almost. There we go. A little better.
All the numbers below, is that what you're saying?
No, the first. So the first n even numbers. If I say sum evens 3, I want you to add up 2, 4, and 6. Those are the first 3 even numbers. Would be 2, 4, and 6. No. If I say sum evens 3, I mean give me the sum of 2, 4, and 6, which are the first 3 even numbers. If I say sum evens 4, I want you to add up 2, 4, 6, and 8.
Oh.
All right?
Starting at 0.
Starting at 0, yes.
I didn't know what numbers
Yeah, I know. I know. In the last class, I totally misunderstood what I even wrote down there. Kayla, you not get this one, or is this recursion in general you're saying?
Oh, no, I got this one.
Oh, good. Oh, how could you get this one and not get it in general? I think you got it in general. I'll give everybody another couple of minutes to finish this up. It's hard. It's definitely tricky. Alex?
Do we have to start at 2?
Start at 2.
Oh, wait.
So what I'm saying is,
I thought that the number of even numbers below and
No, for this one, start at 2.
It's not
That's a different function if you want to start. Yeah. So sum evens 3 means add up 2, 4, and 6.
no, I'm saying is we go from the other way around.
It doesn't matter to me. If you want to, whichever one works. Yeah. I know, we would do a loop. I know, in real life you do a loop. Actually, I shouldn't give this away. On the test, the one you're using is much cleaner with recursion than a loop. OK. Who has what they think is an answer? Yeah, go ahead. I love it. If n equals 0, checking the base case, what are you going to do? Return what? Return 0. Good, base case.
And then return
2n? I can't just write 2n. Well, because that doesn't make sense in programming languages.
Oh, okay.
Times n, yep.
Plus sum evens
Sum evens n
n minus 1.
minus 1. Semicolon, end of function. That'll do it. I'm missing what? I'm missing a parentheses. Thank you. Good. All right, questions on it? You guys had a question? No? Very good. Very good. There are other ways to solve this. This happens to be a pretty easy one. Yeah?
Can you make it if n equals 1, return 2, and then you cut out a single function called the end?
Sure. If you said if n equals 1, return 2, that would work. Yep. That would save you an extra function call. Good call. Yep. This is a little clearer. You might want to comment that and say saving a function call or something.
Wait, so
I would comment that.
you
Yeah.
would add another if statement?
No, you just say if, oh yeah, well, Yeah, you would need another if statement, wouldn't you?
You'd want. No, you wouldn't. You'd never go below 1.
Oh, you'd never go below 1. Well, it depends. What if you asked for some even 0?
Sure.
Or you're not allowed. But yeah, if you're not allowed, you would,
Yeah, what if you put in -1 for this one?
Well, right. If you put in -1, you'd be in trouble, right? This should probably be a little more, probably less than or equal to 0. It probably works a little better in case you're asking for the something that's less than 1, but yeah, or less than 0. What's the least even number? Negative infinity, right, or whatever. Although I don't know if negative infinity is even, but I have a nephew who's 7 years old, and I tried this on him. I never thought it would work because but I tried this on him. I said, actually, wait a minute. No, I have 2 nephews. One's 7 and one's he's 5. And the 5-year-old, I was asking him. I said, what's the biggest number? And he says, 100. And I said, what about 200? And he goes, oh, 1,000. He jumped pretty well. And I go, how about 2,000? And he says, 10,000. And he's like, he's really thinking. And I go, what about 20,000? And you can see him going, oh, what's going on here? And then the 7-year-old goes, it's infinity. and I go, infinity's not a number. And then but I'm like, that's a good answer actually. So it was pretty good. Yeah. But you could see the little brains going, it's kind of nice. Okay, so
there's no answer to that question.
there's no answer to that question, right? Well, I mean, there is no biggest number. You guys know that.
Because infinity.
Infinity's not really enough. Well, go to math class, you find that out. Okay. All right, so that's recursive functions. Let's go on. Stacks. We didn't have a homework assignment on stacks, although we've used them in various forms or another. You should definitely understand what stacks are all about. We've definitely talked about push, top, pop. We're actually, for our purposes, pop is going to return the value and remove it from the stack.
Oh, thank you.
In the standard template library, it doesn't. But for our purposes, pop will both remove it and return it to you. OK? And then is empty will tell you whether or not there's not anything left in the stack. Yeah?
Why doesn't it return anything in the standard?
Yeah, that's a good question. Why doesn't it return anything in the standard? I went and looked that up. It's a kind of a technical reason involving being able to catch when there's an error if the stack is empty. I don't like the answer, but that's the way it is. You can go look it up. There's Stack Overflow. There's a bunch of people talking about it. Good question. OK, we've used stacks for a ton of different things, right? We've used it for postfix notation, right? That's where you had 7 5 times, which would give you 35, right? And we've used it we actually briefly touched on this. You can convert parenthesized infix notation into postfix. And you can also use recursion or use a stack for tree traversal, right? We talked about that in a lab. You actually practiced that for pre-order, I believe, using an actual stack to do the traversal. OK, we can't use it for level order. What do we need to use for level order? A queue, right? You practiced that in lab 2. But you should kind of understand these things.
Do you need to be able to write converting infix to postfix?
No, you don't need to worry about converting infix to postfix specifically. But you should know that that's something you can do with it.
Does it have to be solving postfix?
You won't have to be solving postfix, no. No, if you want to learn a little bit, you're welcome to. It's not hard. Let's see. Explain some stack functions, how they're used. So explain what top. By the way, definitely discuss the asymptotic notation. What's great about stacks? What's the asymptotic notation for everything? Constant, right? That's why we like it. They happen to also be very limited in what they can do. But if you have a problem that uses a stack, you're going to get constant behavior. You should be able to explain how to use a stack to do post-store traversal, that sort of thing. You should be able to use a stack to do something. If I give you a little problem and say program this up using a stack, or 2 stacks, or 3 stacks, or whatever, you should be able to do that. Think through it. Just know that you've only got a few things to do. Stacks are very simple. Push, pop, and is empty. That's all you really need to know. OK. All right. Could we write top with a push and pop?
Yeah.
How would you do it? Pop. Get the value push, right? You could. All right. So be able to use a stack to do something. OK. All right. Then we have queues. And you did a whole assignment on queues, right? First in, first out behavior instead of last in, first out. Right? Queues, insert at the end, remove from the front, just like a human queue. Right? Unless you're Gary Gerst. Let's see. Queues are similar to a stack. There's only a few functions, right? In queue, front, which basically is the same as top. It gives you the front, though. DQ, for our purposes, DQ will give you the value and remove it from the queue. And then is empty. OK? You don't actually need to remove elements as you walk through the queue. Like you don't need to delete them or whatever, or shift anything. You're just going to keep an index to where in the queue you are, the front or the back, and that's that. Circular queues are useful. You should be able to talk through a circular queue question. In other words, why do we use a circular queue? What's the point? What happens if you do fill up the queue? Right? That's the expansion part. OK. And they're the ones that are necessary for level order printing. Yeah?
When you mentioned filling up, is that are we going to assume that queues use dynamic arrays for the test?
I might ask you a question. I'll say building a queue with a dynamic array, blah, 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 right? OK. All right. Are questions on queues? Types of questions we could do. Write functions to create a queue. I might give you, like, here's the data structure you're going to use. Write the enqueue, dequeue, and isEmpty functions. Right? Not too bad. OK. All right. Let's see. So then we go into trees. So we've spent a fair amount of time on trees, and this assignment is testing a lot of that stuff, right? Trees are just nodes with children instead of like links. They are links, but they're not linear. They're like children. There's lots of tree vocab. I'm not going to specifically ask you about tree vocab, but you'll need to understand some of the things. You need to talk about like the height of an AVL tree, blah, blah, blah. But there's lots of vocab. We could have links to all the children, but this is not easy to code, right? By the way, I'm not going to ask you about tries. I decided not to ask about tries. We haven't practiced it yet. Lab is next week on tries, so you do not need to worry about that for this. OK. We could have two like links. One's for like the first child, and then one's for the next sibling. It gets a little odd. It's asymmetric. Works for file systems. You should understand that at least. Not going to make you code it, but you should understand it. And then trees are good for recursive coding. Well, you're learning that right now, right? You can write really simple recursive functions on trees. Okay. All right. Yes. Anna. Yeah, this was the one where we had, so you have some data, and then in here you've got a node that's called like first child, and then a node called next sibling. I'm abbreviating, but you'll have that, right? And then in the tree, right? A, B, C, D, E, and F. A's first child is going to be B, and A does not have any siblings, so its next sibling is going to be null. B's first child is going to be E, and B's next sibling is C, and C's next sibling is D. You see how you can represent the whole tree this way using just a first child and a next sibling, but it is asymmetric. Yeah. Trees can have 3 children, right? Remember, we've got generic trees, which have as many children as you want, right? But then we've also got binary trees, which are the ones we're going to focus on. Yeah. Question?
Shouldn't there, if you've got a pointer to next sibling, shouldn't there be a pointer from B to C?
And from C to D.
And then from C to D?
Yeah, there is. The pointers are in here. I just haven't drawn them up here. This is the tree structure, but underline, like inside the thing, you've got pointers. These aren't the pointers. They're just like the links, right? This is the tree, but the links themselves would be there'd be a link here, and there'd be a link here, and a link here, and a link here, and a link here, and a link here. You see? No, not a link there. I lied. This one does not have a link. Here, let me redraw this without the actual. Let's just draw the pointers, E and F. It's going to be, this is going to be the first child. next sibling, first child, next sibling. That's how it looks when it's all drawn out. OK? OK? It looks like that, and then that, and then that, and then that, and then that. And it's asymmetric. Right? You still can think of it like a tree, but A's children are still B, C, and D. B's children are still E and F. C has no children, D has no children.
A doesn't directly point to C.
Yeah. Why does
A does not directly point to C. Remember, this is the way we're representing it through the node structure.
Oh, because it's only first child.
Because it's only the first child. It has more children, maybe, but the first child happens to be the one that the node is pointing to. Remember, if we're limiting it to only having 2 pointers in here, we have to somehow figure out how to represent any number of siblings or any number of children. OK? Yeah? You could do it for a binary tree. You wouldn't. Like, there's no point, because you can do left and right, and that literally points to the next children. Right? But you could, sure. It would work fine with that. Yeah?
With this, couldn't you then recursively do the print by level that was impossible?
Yeah, these ones you could do recursively print by level. In fact, we did that when we well, you could. This one you could print by level, yeah. Yep. Which I believe is what we did for the first, when we talked about directory structure. Printed by level, yeah. You could. Yep. OK. All right. Binary search trees and binary trees. These are the ones we care a little bit more about. You'll see them all over the place. OK, binary trees are the ones where we just have 2 children, left and right. This can easily degrade into linked list behavior. Why can it degrade into linked list behavior? Because, as we talked about the other day, if you're not balancing them, what's to stop you from going left, 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 or right, 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 right? OK, or right, left, right, left, right, left. Either way, it's going to be linked list behavior. OK, so we have to be a little careful. That's why we like balanced binary trees. We did look at using binary trees for arithmetic, where you can have like plus and 4 and 5, and it means 4 plus 5. Right? You can, if you print that out in an in-order fashion, I'm sorry, a post-order fashion, it will give you postfix. That's nice. OK. Let's see. Trees can be traversed in lots of different orders. We practiced a lot of that. And you should know the differences between them. Yeah?
Is there a difference between a binary tree and a binary search tree?
That's a good question. That question came up earlier today, too. Is there a difference between a binary tree and a binary search tree? What do you guys think? Let's see. Who hasn't answered in a while? Yeah? A binary search tree has an invariant that says all the ones to the left are smaller, all the ones to the right are greater. Yeah, this is a perfectly good binary tree. 7, 20, 9, 7, 2. That is a perfectly good binary tree. Is it a binary search tree? It is not. So you see that difference? Yeah. We will talk about these kind of trees later when we talk about heaps. Not exactly like this, but we'll talk about different forms of binary trees later. OK. All right. So
Do we need to know how to code balance them?
you will not have to balance using code. No. Nope. Binary search trees are this invariant. Thank you. Average depth is logarithmic for a balanced binary search tree. OK. And binary search tree methods that you need to know about find min, find max, contains, insert, remove. And those are all the ones you're doing for your homework assignment. I was talking to somebody earlier. I'm not going to make you code these on the exam, because you're coding them for homework assignment, and maybe you haven't gotten there yet, and you're going to do that. I'm not going to double up on that. So don't go and like, you should learn these because you should know how they work in general terms. But don't worry about it. I'm not going to make you code them on the test. I didn't mention this, but this actually came up in the homework assignment. Lazy deletion is interesting. OK? Let's say that you had a binary search tree that looked like this. 20, and then 40, and then 35, and 50, and 11. If I want to remove 40, OK, I could, let's say these all have a count, right? This is a count of 1, 1, 1, 1, and 1. If I want to remove 40, couldn't I just set the count to 0 and like have it remain in there, but now it's not really there? Like you still need to go by, like past it, and you still need to use the data to know whether to go left or right. But this is called lazy deletion. It means you've removed it from the tree, but you haven't removed it from the data structure.
Is that like kind of what we did when in the arrays when?
Yeah, it's kind of what you did in the arrays when you left items there. It's a little more subtle than that in that this really has to be used still. But it just basically means you're not going through the process of rearranging anything. You're just saying, it's not, it's not there anymore, right? I'm not going to let you do that for the assignment, right? But you could do that. And if you were printing this out, well, then you'd have trouble. Because if you're printing this out, you wouldn't know what to put 35 and 50. Because it's not, there's still something under there. But in the sense of, does 40 exist in this tree? In the logical sense, no. In the physical sense, well, in the computer sense, yes. See what I mean? OK, that's called lazy deletion. Yeah? Okay.
How would that affect the balance of behavior?
That's a good question. It wouldn't really affect the balance or behavior. It would just make it easier to remove. And it would also make it easier to insert 40 again. Right? If you insert 40 now, just move that back to 1. You're done. Right? I mean, let's say you had some use case where you had lots and lots of nodes that you were going to remove and insert lots and lots of times. You might just say, I'm going to just use lazy delete because it doesn't really matter in terms of if they're there or not. If I'm going to be updating to 0 and 1 all the time, might as well do it. So there's some various use cases there. OK? Yeah, good question. All right, so let's see. Binary search trees. You should be able to describe this, right? How do you delete or insert into a binary search tree? Which one's harder? Well, delete's harder. Remove is harder. OK? AVL trees. I am not trying to trick you here. I will give you an AVL tree and say insert a node into it. All right? Practice that. OK? AVL trees are binary search trees. But they're binary search trees with an added invariant that says every node has a left and right subtree that differs in height by no more than 1. OK? First, you insert using BST. And then you might have to do these rotations to make it AVL again. Yeah?
Do we have to know how to code the rotations?
No, you do not know how to need to know how to code the rotations.
So you would just insert it and then just say you have to do these rotations?
No, I would say you have to turn this one. You have to insert it and then redraw this correctly. Yeah.
You're not
OK?
coding.
Nope, you're not coding it. You're just drawing it. So in this case, 14, 7, 4, 12, 11, 13, and 17, and 53. OK, I'm going to insert 8. Where's it going to go?
Under 11.
It's going to go to the which side?
The left.
OK, it's going to go right there. Is this now AVL proper? Which one do we start with checking? Check 8. Well, you first start with the one you just inserted. That one's OK because it just got inserted. This one, is it OK?
Yes.
Sure it is. How about this one?
Yes.
1, 1, 2. It's OK. How about this one? 1, 2. Nope. 1, 2, 3, and 1. This is the one we have to do. Which way do we have to rotate that?
Left.
We have to rotate it this way. Which type of rotation is it going to be? A double or single?
Double.
Why a double?
Because it's the right subtree left.
It's the right subtree's left. How about the right child's left subtree? So we have to first rotate which one?
Rotate
12, which direction? This way. Let's do that. OK, if we rotate 12 to the right, which one do I grab onto? 11. I'm just going to write the part that matters here. 11, and then we don't change the 12. We don't delink it, right? And then 11, nothing's going to change to the 8. But the 12 is going to have what on it? 13. OK? And now if we write some of this other stuff, isn't it as if we had a right insertion? And now you can just do the 7 this way. Well, how do we rotate 7 that way? Grab 11 again. I'll try to do it up here. Grab 11 again, and it's going to be 11. OK? And it doesn't change the 7. But the 8 which came back to 11. What needs to be what with respect to 7? To the right. OK. And then does anything change on the right side of 11? No. 12, 13, like that. And are we out of alignment now? Let's see what's left here. This one is now, did I miss something on there? I missed the 4. 4 here. And then there's going to be 14 and 17. Sorry about the thing here. And 53. Let's see. 1, 1, 1, that's OK. 1, 2, 1, 2, that's OK. 1, 2, 3, 1, 2, that's OK. Everybody's good. OK? Question and then question. Yeah.
I'm just confused as to why when you like pick up the 11 and shake it, 7 and 4 don't just like fall under it.
Yeah, because you don't change this link. I mean, you change it in the sense that you keep 11 and 7 linked together. So if we pick this up, where does 7 have to go if it stays connected to 11? It has to go to the left of 11.
That's because 7 was the one that had.
That's because 7's the one we're rotating out. Yeah. Yeah, that's the way I think of it anyway. I think it's a little easier. Yes? Yes, you will have to draw it. I will say, here's the tree, insert the following, draw the picture in this box. OK? Draw the final answer.
And describe.
Yep. I might ask you to describe what you've done, but I'll just say, I might say, is this a single or a double rotation or whatever? But that's about it, yes. No coding for this. OK? That would take up the whole 2 hours, or hour and 15 minutes or whatever we have. Remember, I'm not going to be here. TAs are going to be administering this. If you have a question that the TAs can't answer, put a note on the test and say, I need to talk to you later about it. That's all. OK? And if there's a million people, then I'll deal with that question in particular. OK? All right, last thing, asymptotic notation. Asymptotic notation is this idea of how fast is a program going to run when we think about big numbers. OK? We disregard the constants, only report on functions that are faster growing. You're going to have to look at functions and a couple of little programs. I'm going to show you one. We've only got a couple minutes, but I'm going to show you one. Here's the ones I care about. Constant up to exponential, log n, n squared. There was a really good Piazza post the other day. Somebody asked about it, and a TA replied, and it was awesome. So you should look at that about this. OK? All right, that's that. Big O notation. Hints. Constant, not dependent on the number of things in the data structure. N is you're accessing all the elements, et cetera. O log n, break the problem into half or thirds or fourths or whatever. OK? You should be able to analyze algorithms. What's the big O notation for that? N squared. You ignore the 5. What's the only one I said you can't ignore? The constant? Tries. Is that what you're going to say? Tries. OK, you want the asymptotic behavior of a try is the length of the word you're searching for. OK? All right, real quickly, I want to show you a couple things. Here's the midterm. You can browse this at your leisure. There's a whole bunch of questions on here. This is the previous one. Here's the actual one. No, not the actual one. You know if it was the actual one, somebody would be slowing the tape down. I mean, like frame by frame. You know. OK, so let's do these real quick. What's the top one? N squared. What's this one? N to the 5th. OK, this one. Let's look at this one real quickly. Because of the time, I'll walk you through it. You're doing some base cases here. And then you're going either left or right. What is that? What is that like? Log n is basically. Somebody earlier today said, hey, what if it was a doubly linked list? And I said, oh, that's an interesting point. I hadn't thought about that. That would be linear. And it'd be a weird thing to do. But it would be linear in that case. But assuming this is assuming it's a tree-type structure, left and right, you're going to be logarithmic. And then this other one, take a look at this one. Who can tell me what the asymptotic behavior for this one is? Yeah? It would not be the length of the student array. Oh, I see what you mean.
So it would be linear?
No, don't worry about that. Don't worry about how long the student array is. Because what are we doing here? We're returning, if you're checking n against an array size, that's 1. That's easy. Checking against 0, that's easy. That's 1. You're not going through the list. You have to go through the list in an array? So what is this one? Constant. Yeah, constant behavior, right? Constant behavior. It's a little tricky. You would just put O1. Yep, O1. Yeah.
There's such thing as, I don't know if you would call it polyexponential behavior, but n to the n.
There is, but I don't know of any functions that meet that criteria. There is, yeah.
So for constant, regardless of like if this was O3, you'd still write O1.
You'd still write O1. Yep. The only one that you wouldn't is if it was like a try. OK? And when you get to algorithms, you might do a little bit more. All right, questions? All right, I will see you guys either in lab or next Monday. Good luck on the test.